Welcome, everyone. Folks are still joining us, but I think we'll go ahead and get started as everyone trickles in. My name is Amanda Graham. I am the Academic Director at the Irving Institute for Energy and Society at Dartmouth College, and I am delighted to welcome you to today's New Energy session. The New Energy series is one that we started almost 2 years ago, actually, to give a platform for young scholars in energy and society from all over the country, and in fact, institutions beyond the United States, to share their work so that there is greater visibility for their current and emerging work, as well as for them to network and communicate and connect with each other. And we have the great benefit of being able to see that emerging work as learners on our end as well. And so we're delighted that you're joining us in this forum today. I am going to introduce Priya in just a sec, but before I do that, I just want to highlight that we're going to be hosted today, moderated today by Professor Justin Mencken, who is a professor of geography and earth sciences here at Dartmouth College, and also the head of our climate modeling and impacts group. So I will hand the mic over to Justin in just one moment, but I'm going to say just a couple of words about our main event, our main speaker today, Priya Donti. Priya is a Ph.D. candidate at Carnegie Mellon, studying computer science and public policy, and I love that combination. So it's a really important one for us as we work to navigate energy transitions. Priya is also the co-founder and chair of Climate Change AI, which is an organization that brings together academics and industrial experts to work on this challenge of how do we leverage machine learning and artificial intelligence for climate solutions and climate improvement, which I think is just a wonderful undertaking that she's added to her CV. She is also a member of the class, the 2021 class of 35 innovators under 30, which is identified by the MIT Tech Review, and she was nominated and selected in the Visionaries category. So Priya, I'm so excited and looking forward to hearing what you have to say today about this really important juncture between AI and machine learning and climate solutions. So with that, I'm going to hand the mic over to Justin to help us get things started. Justin?
Thanks, Amanda. Thanks, everyone, for being here. Particular thanks to the Irving Institute staff, Stephanie and Kristen, and all those who have kind of helped organize, along with Amanda, this really thoughtful series where we're discussing the energy transition with young scholars. Machine learning and its kind of more aspirational umbrella concept of artificial intelligence is really about building models of data behavior from data itself, right? It's kind of a user-guided strategy to identify the rules that govern behavior in data. And the idea is to make a model that's useful for future, right? Where useful can kind of, be, I think, pretty nuanced. The increasing sophistication of machine learning architectures that folks like today's discussant, Priya, have, these things have really only kind of become possible in the way we've seen as late because of recent advances in computing and new insights in the mathematics of optimization or regression, and also, crucially, the much greater availability of data on which to train these models. And on the question of climate change, which is near and dear to my heart as a climate scientist, machine learning, I kind of see it as intervened on kind of the methodological landscape in two distinct domains. The first side is the one I'm familiar with, which is that of the geophysics, where these kind of data-driven deep learning approaches have been used to infer better observations from satellites or replace heuristic approximations that climate models typically rely on to represent physical processes that occur at spatiotemporal scales that can't be explicitly resolved, right? So I'm thinking here most notably of like the representation of the formation of a cloud in a climate model, right? Machine learning has been really essential, and in particular because things like cloud account for a huge fraction of the uncertainty in climate change and in climate impacts. But there are a whole host of other examples, including teams of people who are now building new climate models from the ground up using entirely machine learning approaches. And then the second domain is on the side of kind of the social or human responses to climate risks, where operations, engineers, energy infrastructure managers, water managers, those types of folks are working to kind of optimize management strategies and decisions under resource constraints, right? Like, where do we put our investments to greatest effect? And here I'm thinking particularly of strategies like robust decision making, which is distinct from Priya's work on robustness to adversarial attacks, which I hope maybe at some point at the end in the Q&A she might talk about. And then there's this new body of work, emerging in machine learning and climate change. And I really think that this is where Priya's work is emblematic of this, which is kind of providing a potential path to meaningfully connect the geophysics on one hand and the human on the other, with machine learning as a Rosetta Stone in some way to kind of connect the two. Where Priya is not only considering these strategies to manage climate risks, but the energy intensive domains where machine learning can actually help us optimize a path to a more sustainable, viable, clean energy transition, reducing global warming. Priya, I'm really excited to hear what you have to say. So please take it away.
Awesome. Thanks both Amanda and Justin for the great introduction, and for, again, to all the Irving Institute staff for organizing this. So so I want to spend today diving a little further into some of the points that Justin actually really nicely introduced around what is machine learning, what are the ways it can be used to facilitate climate change, mitigation, adaptation, climate science, and also overarching policy and social sciences frameworks. And then some broader considerations to think about when doing this area of work. I'll also briefly touch on some of my own research, and again, I'm happy to expand upon that in the Q&A. So to start, what is machine learning? So as Justin also mentioned, machine learning is a sort of a branch of this broader area of artificial intelligence. And artificial intelligence refers to any algorithm that allows a computer to perform a complex task. These are usually tasks that we associate with human intelligence in some kind of way, like speech or perception or vision or reasoning. But these systems are not necessarily, at the level of human intelligence. They're often doing individual pieces or small pieces of what we would sort of consider as an attribute of human intelligence. Artificial intelligence spans a really broad set of techniques. For instance, there are rule-based techniques where you actually write down the rules of a particular system and get your computational algorithm to reason over those specific rules to try to figure out what the best course of action is. And this traditionally uses things like optimization, game theory, things like that. And then there's also what is a predominant branch of artificial intelligence today, which is machine learning. And machine learning, rather than these rule-based approaches, concerns itself with extracting patterns automatically from data, and usually large amounts of data. So this is, potentially a very simple concept, right? Get a lot of data, extract patterns from it, but it actually plays out in a couple of different ways that have implications for different applications of machine learning. So in particular, there are sort of three major categories that capture not all of machine learning, but a fair amount of machine learning, and that are useful conceptually to think about. One of these is supervised learning, which is when you have a data set that has labels or answers on it, and you're trying to map from the data to those answers. So an example there might be you have a bunch of images and you know which images are dogs and which images are cats. And your machine learning algorithm is just basically trying to map from the pixels of the image to the label of dog or cat by learning about the mappings that already exist in the underlying data set. Now, this is an example where the reason you would want to do this is because, I could ask Justin or Amanda to, I could hand them an image and ask them to tell me if it's a dog or a cat. I could do this with 20 images. By 100 or 1,000 images, they would probably get pretty annoyed with me. So the idea is that machine learning here is scaling human intuition or human knowledge at a much larger scale, often a little bit imperfectly, but at a larger scale. Another paradigm for machine learning is unsupervised learning. And this is where you have a data set that does not necessarily have labels on it, but you're trying to uncover some kind of underlying structure in the data. So clustering is a good example of this. Imagine you have energy usage data from a bunch of different homes, and you want to get a sense of which customers are similar to each other in terms of their energy usage patterns. You don't have labels in terms of this is customer type A or this is customer type B. But by using clustering methods, you can figure out, okay, which groups of consumers are maybe similar to each other in terms of their energy use. So this would be an example of uncovering some kind of structure in your underlying data, which is where unsupervised learning techniques come into play. And then a third branch is reinforcement learning. So where for supervised learning and unsupervised learning, I mentioned the fact that there sort of exists a fixed data set that you're trying to derive insight from, though in different ways. Reinforcement learning is a setting where you don't actually have a fixed data set, but instead you have some kind of environment and some kind of agent that's acting on it. So for example, you can think of an environment like being an electric power grid and the physics of the underlying electric power grid. And your agent might be a battery that's figuring out how to charge or discharge on that power grid. And what reinforcement learning does is basically say, let me try out a bunch of different actions and let me see how good they are. Let me charge or discharge my battery and figure out what the pricing implications of that are, what the reliability implications of that are. And based on getting that signal from the environment, then adjusts its own behavior and learns how to sort of do this better, how to take better actions like better charging or discharging of battery kinds of actions. So I wanted to give this perspective because, again, just when people think about machine learning, they often think of a very specific use case, like machine learning can help sense satellite imagery or machine learning can help control a power grid. And these are different. This is basically a taxonomy that can help you conceptualize different ways in which machine learning might actually play out. And before I go into the direct connection with climate change, I do want to point out that, of course, machine learning, like any other tool, has its own strengths and limitations, and these have to be taken very fundamentally into account when actually using these tools for climate strategies or really for anything else. So its strengths include scaling human insight. So I mentioned this supervised learning example where, if I ask a person to label 1,000 images for me, they'll get really annoyed. But if you ask them to label a few, then a machine learning algorithm can learn from those labels in order to infer the labels of a bunch of other images. So machine learning is good at scaling human insight. Through reinforcement learning and other paradigms, it's also good at optimizing complex systems. For example, the battery charging example I gave earlier. It's often been used to generate sort of new or derived data, or another way you can think of it is turn raw data into actionable insights. For example, take satellite imagery and use that to generate, for example, crop type maps or information about the locations of solar panels, things that we can then actually use for decision making. And recently, there's also been some innovations, and this is also where my work comes in, that actually try to integrate machine learning with other methods. So Justin, for example, mentioned ways where machine learning is being used to, for example, approximate the formation of clouds, and then that gets embedded within a climate model. Some of my work's at how do you actually embed the physics of a power grid into a machine learning model, but there started to be these new techniques that actually embed traditional optimization and physics within machine learning or vice versa. On the other side, of course, machine learning has a lot of limitations. Because machine learning fundamentally is a paradigm where you're learning from data, if your data are bad, then your insights are going to be bad. And so this is called garbage in, garbage out. In addition, if your data is biased, then your algorithm's predictions will be biased. But beyond that, there are often many assumptions and biases that we bake in when we actually design these methods, or when we figure out what kinds of questions we're actually asking that we're asking these methods to answer. There are lots of biases throughout that entire system. And machine learning algorithms, not only they don't mitigate them, but they often can exacerbate those kinds of biases. So it's really important to think of machine learning algorithms as not being objective, but instead accelerating and making more efficient the systems in which they're employed. And so thinking about what those systems are and what the attributes of those systems are becomes very important. In addition, machine learning assumes patterns are persistent, which is to say, if you give machine learning algorithms some data, they assume that that data represents the world and all of the patterns represented in that data represent the world. And if you try to employ the machine learning algorithm in a situation that looks fundamentally very different, it's not going to do well. So to give a concrete example of that, if you, for example, trained an electricity demand forecasting algorithm before the COVID-19 pandemic, when our energy usage patterns looked very different, and you try to employ that model during the COVID-19 pandemic to predict electricity demand, the model is not going to do well because the data it was trained on are fundamentally different than the sort of real life situation in which that model would be used. And then last but not least, machine learning methods are in some sense statistical methods. And in your stats classes, you might have heard, right, like these methods tend to find correlation, not causation. And for machine learning, this is also true. Machine learning methods find correlations in the data, but they can't really tell you anything about the causal patterns of the underlying data. Now, there is a sort of whole research branch in causal machine learning trying to figure out how to actually draw causal inferences from machine learning methods, sort of in the same way that similar threads exist in econometrics. But again, this is sort of an active area of research rather than something that kind of natively gets spit out from your machine learning model. So with that background and all those caveats, I now want to dive into talking about how exactly machine learning and climate change are connected. And specifically, I want to start by talking about different ways in which machine learning can be employed to address climate change. So about 2.5 years ago at this point, a group of researchers and I wrote a paper called Tackling Climate Change with Machine Learning that tried to address exactly this issue. And in, a succinct 100 pages, we describe different ways in which AI and machine learning can actually come to bear in this particular in addressing climate change. The paper is available online for those of you who want to check it out. And there are also some summaries available online at the URL at the top of the slide where you can sort of filter by different sectors or by area of machine learning method and things like that. And in the paper, we basically talk about various ways in which AI and machine learning can help with both mitigating climate change, so reducing emissions from electricity, buildings, transportation, agriculture, forestry, and industry. Ways in which AI and ML can help us adapt to a changing climate by doing things like enabling more localized climate predictions or helping build more resilient, ecological, infrastructural, or social systems, or by facilitating disaster response. We also talk about how AI and machine learning can help foster policy strategies or social sciences strategies by providing insight to these strategies in order to sort of enable the implementation and transition to these kinds of methods. And we also talk about applications in climate science, so how you actually model the climate and how it'll change over time. So while this paper contains, dozens of different applications, there are a few key themes that emerged across these applications that I'd like to share as a way to also, again, conceptualize how AI and machine learning can play out here. So the first theme here is gathering information. So there are lots of situations in which a decision maker might need some information to make a decision about, for example, climate policy or about some kind of action that would service a climate change or mitigation or adaptation strategy, but where that relevant on-the-ground information may not already be readily available. So there have been a lot of applications using AI and ML to gather proxies for this information that might not exist, by analyzing large streams of data like satellite imagery or large corpora of text documents. So for example, there's an international coalition of organizations called Climate Trace that's currently trying to pinpoint the sources of greenhouse gas emissions and create more transparent estimates of what global greenhouse gas emissions from different sectors are, using a combination of satellite imagery and other sensing. And the goal is to inform climate change policy, and in this case also, UNFCCC, like the negotiations that go on under that umbrella. There are also initiatives to try to do things like pinpoint deforestation or map solar panels or understand crop yields for climate change adaptation purposes from satellite imagery. So the image on the slide is an example of a crop mapping application. In addition, I mentioned sort of text applications. So there's a nonprofit in the UK called Climate Policy Radar that's currently trying to use machine learning to analyze policy documents and policy texts at scale in order to derive insights from those that can be then used for data-driven decision making. So in all of these cases, the goal is to take some large available data that would be really difficult to analyze manually and use that to derive insight or derive proxy information to serve as a substitute or a placeholder in cases where that information doesn't already exist in order to inform some kind of decision. So another key theme is forecasting. So of course, there are many situations in which foresight can help to make a better decision. So things like this include machine learning, taking historical data or taking information about videos of the sky and cloud cover in order to predict things like how much solar power will be available in the short to medium term. And this can help us basically better manage electric power grids in order to maintain the balance between electricity supply and demand if we can be more confident in our supply and demand forecasts. There are also applications here of machine learning to forecast things like transportation demand to inform transportation system planning, and also creating localized forecasts of extreme events in order to enable better disaster response policies at the local level. There are also a lot of applications where AI and ML can help increase the efficiency of a real-world operational system. So for example, heating and cooling systems make up almost half or more than half of the energy use associated with buildings. And there are lots of applications associated with optimizing heating and cooling in residential and commercial settings. There are also applications in optimizing freight and supply chains to reduce the emissions associated with those, and also things like even optimizing food purchasing systems and refrigeration systems for food in order to reduce food waste. Similarly to that, there are lots of inefficiencies in real-world systems, and analyzing large-scale sensor data can help us identify those efficiencies either in real time or proactively before they become a problem. So this turns up in areas like detecting methane leaks and natural gas pipelines, where of course methane is a really potent greenhouse gas, and also in trying to make infrastructure resilient to, for example, extreme events that are exacerbated due to climate change by using sensor data to understand what might happen to the infrastructure ahead of time. So the image on the slide here is actually an example from Deutsche Bahn, the German rail operator, where they actually use a combination of large-scale sensing and AI for predictive maintenance, to basically proactively identify faults in the underlying train system in order to help, facilitate the efficiency of trains and therefore make rail a sort of, the low carbon transportation form of rail more efficient and more competitive relative to transportation in other sectors or transportation of other sorts. So another way in which AI and machine learning come into play is by accelerating the search for clean technologies, or so accelerating scientific experimentation. As we attempt to create sort of a new clean technology, so for example, next generation batteries or solar panels or electrofuels, there's a lot of experimentation that goes into that in trying to figure out, okay, I have a bunch of experiments where I've tried to synthesize batteries in the past. What battery am I going to try next to synthesize? And the issue with the traditional form of scientific experimentation here is that these design cycles take a really long time. If you want to design a battery and then test it out, that process takes months to actually just even see test results that make sense or that can actually verify the performance of the battery. And by the time you've gone through that one design cycle and then tried the next one and tried the next one, you're looking at many, many years to design even one viable battery for a particular use case. So what AI and machine learning do is they say, well, let's analyze the outcomes of past experiments in order to recommend what experiments we should try next. And this can basically help cut down the number of design cycles by making sure that each experiment is as effective in getting more information as it could possibly be. And companies like Aionics, based out of the Bay Area, have actually seen that as they've worked with battery manufacturers to actually implement these techniques, they've actually been able to cut down the design cycle times by about a 10x factor. So that's really cool. And then a last theme I want to mention is approximating time-intensive simulations. So Justin mentioned this to an extent where we, in climate and energy scenarios, we have things like large-scale climate models that are really time-intensive and energy-intensive to run, and they can only be really run at large spatial resolutions, for example, because they're so computationally intensive. So AI and machine learning, as again Justin mentioned, have been used to approximate portions of these models, for example, things like clouds, in order to make those particular portions less expensive and less time intensive to run. And then you can integrate that sort of cheaper proxy for your cloud physics into your broader model in the hopes that it reduces the running time of the overall thing. So that's a climate modeling example, but this also comes up in power system optimization, planning models, city planning models, or models that try to simulate the urban microclimate. There's, for example, a team at the Austrian Institute of Technology that developed something called infrared, which basically is a deep learning proxy for an urban microclimate simulator, which they can use to then figure out how to best place buildings and design building attributes to both reduce the energy consumption of those buildings and also adapt to heat waves as they become more common due to climate change. So these are some recurring themes to just try to give a picture of the different ways in which AI and machine learning can play a role in facilitating other strategies from climate change mitigation, adaptation, and climate science. I'm going to go into some important considerations and caveats to think about when implementing these kinds of applications. But before I do that, I want to dive into a little bit of an overview of my own work, how I actually use AI and machine learning techniques, specifically in the context of electric power systems. So in electric power systems specifically, there are lots of ways in which AI and machine learning can come into play, sort of drawing across all of the different themes that I talked about on the previous slide. So this includes things like providing better forecasts of electricity supply and demand, providing maps of power grid infrastructure where we don't have information about the location of things like solar panels and transmission infrastructure. And also the area that I also work on is optimizing and controlling electric power grids more dynamically and more quickly in order to foster the integration of renewable energy. What we're seeing on electric power grids today is that we have traditional optimization and control methods that are good at sort of enforcing some of the physics and constraints and decision-making procedures that we need to enforce on the electric power grid. But these methods are increasingly slow or just failing to deal with the speed and scale and introduced complexity with which we need to manage the electric power grid, given the introduction of stochastic and variable renewable energy. So machine learning has been called upon to say, well, can machine learning provide more dynamic, data-driven, and faster methods to optimize and control electric power grids? But the challenge with these methods is that machine learning, being completely data-driven, doesn't necessarily have inbuilt mechanisms to enforce the physics or hard constraints associated with electric power grids. So for example, if you use a machine learning model to approximate power system optimization models, this approximation might not satisfy the power flow equations. It might fundamentally violate the physics of how power flows on the grid, and that can lead to huge issues. So what my work actually does is try to bridge machine learning techniques with these existing techniques in optimization and control to try to get the benefits of both of these worlds, to basically say, can we come up with a fast, dynamic, and data-driven method, but one that uses techniques from optimization and control to actually capture the physics that we need to capture. And so the mechanism I do this through is by something called optimization layers and neural networks, basically providing ways to embed optimization problems that traditionally represent things like the physics of the power grid into the way that we design deep neural networks, deep learning, machine learning methods. And at a high level, there are a couple of, basically my work basically provides a way to say, if you have physics or hard constraints or decision-making procedures that you can somehow encapsulate as an optimization problem, then I can tell you how to embed those into your machine learning model or into the objective, the signal that is used for that machine learning model to learn. And in power systems, this plays out in several ways. One of these is decision cognizant demand forecasting. So when we make electricity demand predictions today, we tend to try to make them as accurate as possible. And while accuracy is a good goal, if you get a perfect prediction, then you'll probably make a perfect decision on the basis of that. The kinds of mistakes that an accuracy optimizing model will make are not necessarily the kinds of mistakes that are okay from the perspective of the downstream decision-making process. So to make that really concrete, imagine you're forecasting electricity demand. If you're trying to create a forecast that's as accurate as possible, then under-predicting demand and over-predicting demand might feel exactly the same. So from an accuracy perspective, an under-prediction and an over-prediction are the same. But if you think about the implications of those different kinds of mistakes for the decision-making process when you're actually trying to schedule power of the electric power grid, an under-prediction might lead to underscheduling of electricity supply, whereas an over-prediction might lead to overscheduling of electricity supply. And in many ways, underscheduling is a much worse outcome than overscheduling. So what my work does is say, can we actually figure out, if I make a prediction, how will that prediction be used to make a decision? Let's write that down as an optimization problem and actually bake that into the way we create the demand predictions in the first place, so that our forecasting model can avoid making mistakes that are really bad from the perspective of the decision maker. So that's one kind of thing that I do in my work. Another thing I do in my work is try to provide fast and feasible approximations to power system optimization models. So these are things like models like AC optimal power flow or security constrained optimal power flow, basically different kinds of optimization algorithms that are used to manage the electric power grid, where running these algorithms is really important to managing a power grid. But as you have more time varying renewables, you need to run these problems more quickly and at larger scale, which just traditional optimization methods are really struggling to do. So what my work does is say, let's try to approximate some aspects of these optimization models using machine learning, and then bake in some information into our machine learning model to make sure things like our power flow constraints or other physics in the underlying power grid are actually satisfied. And I do this through the use of embedding optimization within neural networks. And then the last example I want to give is on the control side of things. So as you're trying to control distributed devices like solar inverters, you want to do this in a way that optimizes some notion of performance. So for example, reduces curtailment of renewable energy sources. But you also want to make sure that you're maintaining the voltage on your power grid, that you're in some sense maintaining some kind of equilibrium state on your distribution system so that you're not degrading the equipment on your distribution system. So traditionally, you would do this using traditional control theory, which is really good at, for example, ensuring that you don't destabilize your distribution system by making sure your voltage magnitudes stay close to 1. But these methods tend to be really simple, and as a result, curtailment might be higher than you want it to be because it's prioritizing stability over performance. So my work brings in techniques from reinforcement learning, from machine learning, then I can actually learn to do something clever and nuanced and actually increase performance in terms of reducing curtailment while still preserving the same stability and robustness guarantees in terms of voltage control that robust control methods used to do. And again, this is by formulating certain robust control criteria as an optimization problem and embedding that into the way that you design your machine learning method in the first place. So these are just some examples of how kind of my work basically tries to bring together machine learning with other areas of study like optimization and control in order to try to get the best of both worlds and sort of keep our traditional safety and physical guarantees while bringing in better performance using machine learning methods. And in general, a lot of work in this machine learning for climate change space has this kind of flavor, where you're really trying to not just use a brute force data-driven method that learns on some random set of data and provides some kind of output, but where really we see that there's a lot of value in merging both the traditional approaches that have been used in a particular area with some of the newer data-driven approaches that are coming into play. So given those examples of both, the broader work that exists at the intersection of AI and climate change, and also what I'm specifically working on, I want to go into a couple of important considerations for thinking about this relationship between AI and climate change. So when we think about AI and machine learning in context, many climate change strategies don't need AI or machine learning at all. So this is my talk here is not trying to say that AI and machine learning are a silver bullet, or in fact that they're in any way exceptional, but rather that there are some places where this large scale data driven analysis can really, supplement existing climate change strategies. And in general, where AI and machine learning are applicable, they're only one part of the broader strategy. If I, send solar panels from satellite imagery, that's great. But if somebody doesn't use that information to do something useful, then no real climate change related strategy has actually been actualized. And so this plays out in a lot of different places. And a lot of the impactful applications in this area might not be flashy. So there are some moonshot applications here, like AI and machine learning for batteries, or even AI and machine learning to discover nuclear fusion technologies or to facilitate nuclear fusion development. But there are also applications on the other side of the spectrum, like predictive maintenance. Let's just make sure our existing infrastructure doesn't break, and sort of addressing applications across this spectrum, all the way to sort of moonshot scientific discovery to last mile deployment, of course, becomes really important when we're thinking about a holistic portfolio of strategies to address climate change. And in terms of deployment, there's a huge variety in terms of the kinds of AI and machine learning methods that exist. There are really state-of-the-art complicated methods, and there are really simple methods, and sometimes simple methods just work. And there are lots of reasons to favor simple methods where they do work, because they tend to be more interpretable or easier to debug and all of those kinds of things. With AI and machine learning, and really any other technology that improves the efficiency of a system, we also have to be, of course, aware of rebound effects, where if you make a system more efficient, some of that saved energy or emissions might come back through increased usage. And so baking in ways, both through the way we design our algorithms, but also through, of course, broader policy instruments that we might use in a particular setting, we want to be aware that, we want to maybe mitigate the effects of some of these rebound effects. Another big consideration to keep in mind is that AI and machine learning techniques right now, a lot of the skills, infrastructure, compute power, all of those kinds of things that are needed to develop these methods are actually concentrated within a select set of entities, often in the developed world. And whereas, of course, climate change related strategies have to involve everybody across the world, not just those few who have access to these kinds of resources. So when thinking about the design of AI and machine learning algorithms, thinking about the framing of problems that might be solved, which stakeholders' problems we're solving, who can access solutions. In all of these things, we always have to think about this in the context of climate change. But in the context of AI plus climate change, some of these considerations become all the more important, all the more acute. And as a result, of course, partnerships are key. So partnerships across researchers, implementing industries, end users, policymakers, and also other affected parties, those who might not be directly parties who would be the ones implementing a solution, but those who might be affected by it. Of course, it's important to make sure that they're sort of, included in the overall process here. And one of the last things I want to say here is that while I've talked so far about how AI can be used to help facilitate climate action, for example, through applications in climate change mitigation and adaptation, AI is a multi-purpose tool. And as a result, it can actually have both positive and negative implications for climate change. So these include things like AI applications that increase emissions. For example, billions of dollars go into using AI to facilitate the extraction of oil and gas and accelerate extraction and exploration. And this can, boost reserves, reduce costs, and otherwise make oil and gas relatively more competitive compared to some other sources that may exist. So it's really, we're thinking about, there are lots of ways in which AI and machine learning are basically being used to accelerate emissions intensive industries in a way that sort of entrenches the roles of those emissions intensive industries. There are also many AI applications that we often don't think of as directly climate relevant, but that nonetheless have relatively large climate impacts. So for example, AI is widely used in recommender systems that actually target advertisements to individuals and entities to increase their consumption. And of course, these consumption increases potentially have large implications for the emissions impacts of our societal activities. there are also many places where AI is a key technology within a broader technology, something like autonomous vehicles, and the direction in which this technology is developed can have positive or negative implications for the climate. For example, if we develop AI and autonomous vehicles in a way that entrenches the role of private and fossil fuel transportation, that can potentially increase emissions, whereas if we do this in a way that really bolsters low carbon and public transportation, then this can decrease emissions. So AI and the broader technologies in which it sits can there are many choice points where we can really shape what the emissions implications end up being. And last but not least, the use of AI itself has energy and emissions implications, both through the, when you're running an AI algorithm on computational infrastructure that draws power, which is produced, of course, through electricity that is potentially emissions intensive. And then also the hardware itself has embodied emissions associated with its manufacture and transport and so forth. On a macro scale, the emissions of the ICT sector are something like 1.5% to 2% of global greenhouse gas emissions. And AI itself is a really small fraction of that. So in some sense, on a macro scale, the impacts of the applications really overwhelm the impacts of the energy use itself. But the trends are such that AI models are growing, they're starting to use more and more energy. And in general, we of course want all of these sectors to, for example, go to net zero by 2050. So we really have to think about this picture holistically when we're trying to shape strategies for actually shaping the development and deployment of AI going forward. So in service of that, a group of colleagues and I actually put out a framework for impact assessment of AI, which is forthcoming in Nature Climate Change. And basically this provides a way to conceptualize AI's effects on greenhouse gas emissions, provides some notes on the numbers that exist and the numbers that we would need to exist, and how we can actually shape impact assessment and data collection frameworks in order to facilitate that. And more broadly, work in this area of AI and climate change is going to require participation from across academia, industry, the public sector, and civil society. And so a group of us recently wrote a report for the Global Partnership on AI, which is a multi-stakeholder initiative of the OECD, to basically try to provide recommendations to governments and international organizations as to how they can both foster the use of AI for climate action in places where it's appropriate, and also shape AI's impact and reduce AI's negative impacts on the climate in places where that's happening. So for those of you who are interested, I'd encourage you to check out this report. And then finally, as was mentioned in the introduction towards the beginning, if you're interested in thinking about these kinds of issues and these kinds of topics at the intersection of climate change and AI, I'd encourage you to sort of join into the Climate Change AI community. So Climate Change AI is a nonprofit organization drawing, again, participants from across academia, industry, and the public sector that tries to basically foster education, team building, and provide infrastructure to do impactful projects at this intersection of climate change and AI. So for example, we hold a regular workshop series at the major machine learning conferences, and alongside those hold mentorship programs so that if you're somebody who wants to get into this space and has expertise in either machine learning or a climate relevant area, but not the other side, we can pair you up with a mentor with complementary expertise in order to help shape research and projects in this particular area. We also provide, global research funding for impactful projects. So recently ran a $2 million grants program, and also maintain an online community, newsletter, webinars, happy hours, and so forth to help you meet other people and learn more about work in this space. So for those of you who are interested, I'd encourage you to check out the website. So with that, thank you so much for listening, and I'm really looking forward to the Q&A.
Priya, that was totally awesome. I learned a tremendous amount. I'm really, really grateful for that. Just really thorough survey of, just how many pieces of work you have going and the big thinking you're doing about, what responsible use of AI and machine learning looks like to kind of, push for solutions to climate change. There have been a couple of questions that have come up in the Q&A. I mistakenly chatted to everyone that they should put their questions in the chat. The chat is disabled. Please use the icon that says Q&A at the bottom right of your Zoom window to go ahead and type in your questions. You've covered a lot of things Priya. And there are a couple of things that I wanted to just kind of pull on a little bit more, if that's all right. You kind of throughout, there's this interchangeability between kind of AI and machine learning. And I just wondered if you could talk a little bit more about the distinction you see there, just in terms of your work. Like, what does it look like to go from these kind of user guided machine learning techniques where, you know, these choices are being made, whether you're using kind of deep learning, you know, like I've employed temporal convolutional neural nets in satellite data, and there are a ton of choices that need to be made. How we kind of go from that to actual AI, where the questions, maybe even the data, the architecture itself are kind of emergent from the learning process. Like, how do we do that, particularly as it relates to some of the problems that you're tackling in your work?
Yeah, so that's a great question, and it probably a bigger one than I'll be able to answer here, which is to say there are lots of people who, like right now, if you create a deep learning architecture, this is done very much by hand. People use techniques like neural architecture search, where you're really just trying out and brute forcing a bunch of different configurations before you can see what actually works. So I think the leap from that to really something that's self-configuring is really high. And I think we're honestly very far from it. There's some people who are thinking about how to get there, but there's a lot to do before then. And so right now, when I think about AI and machine learning, I really do think of it in somewhat more of this hand engineered domain, where whether we're in this hand engineered domain or this fully automated domain, we really want to think about what are the values that we are implicitly or explicitly embedding in the way that we actually design these, and what are the assumptions that we're actually embedding. And it's sometimes hard to evaluate and hard to see. But this is also why many people are calling for not just when you design an AI method, but when you design it, thinking through what is the evaluation structure that you're going to use, how are you going to evaluate its performance, and how can you sort of continue to, as you deploy it, continue evaluating performance, continue evaluating whether the algorithm is doing what you want it to do, in order to use that to tweak things. So I know I took that a little bit orthogonal to what you had originally asked, but just sort of given that we're so far from these really self-configuring, fully autonomous things, this question of understanding the values that you're baking in becomes all the more important in the meantime.
Yeah, no, that's helpful. I mean, I think, you know, in some ways, kind of the term of art AI itself, you know, it kind of holds, you know, the popular imagination in a different way than a term like, you know, machine learning might. And so, like, I wonder, for you as, you know, a scholar of this, like, that the interchange of those words based on the communities to whom you're speaking, and I mean, you know, and you can see that also, I guess, in the publications too, right? Like the kind of public facing side is kind of thinks of it as AI, but, you know, the back of the house technical side, it's really in the weeds on the loss functions being optimized or what have you, which are
That's
machine
right,
learning
yeah.
themselves, right?
Yeah.
So it's just an interesting communication thing.
Yeah.
So we have a couple of questions coming in. So I kind of took prerogative. I have a bunch more, but I will ask some of the ones that are in the Q&A that we have here. So one of them says, at the public level, to what extent do public representatives or private companies actually consult with experts like you before establishing things like new infrastructure, and presumably the deployment of machine learning approaches to the optimization of that infrastructure, right? I mean, the technical capacity required to responsibly wield the power associated with these techniques is considerable. And the danger of the democratization of these machine learning techniques is that you have a bunch of people who don't actually understand what's going on under the hood using them to ill effect. So,
yeah. And this is great. And with all, of course, like questions in public policy, the answer is invariably it depends. So there are, for example, some entities in the electric power sector, RTE France comes to mind, where what they're really doing is they actually established a challenge series within the AI community, within the machine learning community, to basically say, we want to see whether reinforcement learning is potentially a viable tool to help us semi-autonomously manage our power grids. So let's create a simulation environment. Let's create a challenge problem around it. And let's take that to the machine learning conferences and get these practitioners and researchers to actually try this out. So that's a really, in some sense, it's a very direct form of consultation in the sense of, this is the need we have. Let's see, get a bunch of people to actually try it out and show us what can and can't be done with these kinds of techniques. And on the other side, you have, sort of on the other side, you have entities that have sort of realized that AI and digitalization are going to be really important in, for example, shaping the electric power sector. But because of how networks of people and things like this work, a lot of the consultation is done with stakeholders who are either in the electric power sector or tuned into the power sector. And unfortunately, as of now, in some sense, the AI and machine learning community is often less likely to participate in task forces and public sector kinds of initiatives. So anecdotally, for example, many people, after a PhD, they might participate in a AAAS fellowship to actually work in Congress for a year after a PhD. And the representation of people from the sciences and engineering is much larger than the representation of people from computer science. So I think there's really a lot to be done to get people on the computer science side to actually embed themselves in these existing mechanisms that do exist for public input. So basically it depends. And there's some existing routes. There are some places where routes should be established, where there should be, for example, digital task forces established in certain places, which is actually one of the policy recommendations in that GPA report. And there are other places where I think it's a communication issue, trying to just get people to take advantage of some of these routes that do exist.
Do you think, given your career stage and kind of your thinking about the portfolio of options you have in front of you, right? Like, what if there? It's not just about kind of the identification of the opportunities, but also maybe a changing of incentives. Like, what are the incentives for highly skilled, really well-trained people who understand these algorithms inside and out and their appropriateness and the kind of model for purpose type adage that we as modelers hold dear, so that these things are responsibly wielded in these public domains where like what is the incentive there, and what can organizations kind of do to create some incentives?
Yeah, so money becomes a huge, of course, incentive. If you're an undergraduate in computer science, you can make a six-figure salary right out of undergrad by going and working at a tech company or in finance. And in many places like the electric power sector or in public policy or in other places, that salary just, it is hard to compete with that. And in addition, even within the tech sector, when you look at, for example, climate tech startups that exist today, a startup is not really able to pay an employee the same amount that maybe an established tech company could. So some of this is finances. Some of this, though, is, I think, again, communication, in the sense that if you talk to a computer science undergraduate and ask them what their next steps are, the thing is, are you going to go academia or industry? And when people say industry, what they mean is the tech sector or finance. And there isn't really an awareness of what these other routes are. When you look at the job fairs that undergraduates can go to in computer science, there often, there's a huge overrepresentation of tech companies, finance, and defense. And you don't have some of these other companies that might benefit from, for example, computer science undergrads represented at those, in part because it, for example, can actually be expensive to buy into collegiate job fairs, and not everybody has access to that. So I think somehow, creating incentives, there have to be some ways to think about how to make some of these paths maybe more financially attractive, or to even that balance out, but also to raise awareness of some of these paths by providing feet in the door to those entities that maybe should be put in front of, for example, undergrads, but are currently not. Yeah.
Certainly money, but it's kind of, where the awareness intervention happens too in someone's career, I think is really important. I think there's also, a question that I think relates that just popped up, it's not just on the machine learning practitioner side, but kind of everybody else, right? Somebody who might, have a need for machine learning to, potentially solve a problem that they face as a decision maker in the public or in the private sector. Kind of what should the kind of general public who are going to be becoming increasingly reliant on machine learning to be solving various problems. I mean, all of the ways in which machine learning is already solving a lot of problems that people are not aware of. Like what's kind of the baseline level of skill or understanding that someone should have about this. I think that's like an interesting question, like this idea of fluency. And statistical fluency is really lacking in our society, and the communication of risk is really a problem because of that. And so, yeah, just what does it look like to educate the wider public?
Yeah, and I would say a lot of these questions around AI and machine learning algorithms are also similar to fluency in statistics. So understanding things like for sort of what is an AI or machine learning algorithm? What are the kinds of things that it can do? What are some of the pitfalls in terms of data or things like that it can fall into? And what are some things that it either can't do or isn't a replacement for? And in some sense, some of these introductory slides that I gave on AI and machine learning represent the broad thrusts of the kinds of literacy that I think are important, or the kinds of concepts that I think it's really important for people to grasp, even if they're non-experts in this particular area. And then that question also asks inversely, to what extent are AI and machine learning people well equipped to actually communicate their work or results? I think there's a lot of work to be done there as well. And in particular, one issue is that because AI and machine learning are so flashy, it gets to the point where if you have even a half-baked thing that works half well, you probably get tons and tons of media attention. Whereas somebody who, does something that is, much more nitty gritty in terms of, oh, great, we found a better way to, create a solar power inverter that doesn't break. That's just not going to make the news in the same way. So I think there's also both we as AI and machine learning folks need to be careful and holistic in the way that we communicate and make sure that we're also talking about what the alternatives are in any particular scenario and what the limitations are. But I also think it's really important from a public communication and media perspective to make sure to kind of appropriately elevate these different narratives so that AI and machine learning doesn't disproportionately get a bunch of attention just because it's flashy.
Yeah, that's great. Thank you.
Yeah.
You kind of raised it a little bit at the end there when you were kind of going through the very reasonable laundry list of kind of limits of AI. And I wanted to talk a little bit about AI and justice for just a second, if possible. Like the proliferation of data in today's world, like I think it's an appropriate question as to whether or not it's like a democratic and like equalizing force, or if it's just, kind of a manifestation of existing systems of power and profit. And I think you kind of intimated at that, right? Like, and since these models are so reliant on the data that's collected, and you kind of motivated your whole talk with like a very common adage in modeling, which is garbage in, garbage out, right? And it's like and if what gets measured gets done, right? Like from a policy perspective, I'm just wondering about the things for which there are no data, and how an enhanced reliance on machine learning and AI to kind of identify solutions leaves things out, and how we machine learning practitioners can be more aware of the limits of AI as kind of this silver bullet for societal ills.
Yeah, no, there's a big question in there. So I guess I mentioned somewhere in the talk that AI and machine learning are accelerators of the broader systems in which they're implemented. And so thought about what those systems are can be a really key component of understanding whether AI becomes an exacerbator or an equalizer of inequities. So for example, if you're using these kinds of techniques to optimize industrial agriculture, in order to facilitate large-scale factory farming, there might be good reasons to do that. But if this is being done exclusively instead of doing things like also providing data-driven insight to smallholder farmers in order to help them foster their their farming practices, then you're creating an inequity. And in a way, it's interesting. A lot of these, process efficiency kinds of applications are ones that I think entities with larger amounts of resources are able to take on. But a lot of these applications where it's turning raw data into actionable insight can, if used properly, I think really be an equalizer in some ways. At one of the last COPs, one of the last UN climate change conferences, I was talking to a couple of stakeholders from a developing country who were basically saying, we need on the ground data, but we're not getting funding for sensing to actually install that sensing and collect that on the ground data, because we're being told we need to demonstrate what the value of that data is in order to justify the sensing. And it creates this chicken and egg problem where without the data, they can't justify that value. And without justifying that value, they can't install the sensing. Whereas doing something like using satellite imagery to get some proxies for that information can provide at least an initial basis to see what that value might look like before then implementing this forward. So I think there's some carefully placed applications where really you can use these kinds of techniques to break information asymmetries or information inavailability that might stop a process from going forward in a way that enables you to actually start that going forward for a set of stakeholders with fewer resources.
Wonderful. Really, thank you so much, Amanda. I think I want to turn it over back to you. For those that didn't get your questions answered, I assume you should reach out to Priya directly, or maybe we can facilitate to make sure that those get answered for you. You can email me and I will reach out to Priya.
For sure. I've stuck my email address in the chat, and I also tried to answer a couple of the questions in the text, but absolutely feel free to reach out.
I want to thank you both so much. Priya, this was fascinating, informative, not just for on your own work, but also on how we can think better about AI and how we can deploy it better for social good. So Justin, I really want to thank you for moderating the talk today and for your observations about the relationship between AI and climate. And Priya, again, fantastic contribution to our series. Thank you so very much for this, and all the best to you as you continue on with this really important work.
Wonderful, and thanks so much for organizing this and for the great initiative overall.
Absolutely. If we could pull up, Stephanie, our slide, there's a few additional events I want to highlight to folks coming up. So if you are looking for something on April Fool's Day, we have at Dartmouth a seminar on low carbon energy R&D portfolios with Erin Baker from UMass Amherst. Next week, our Dartmouth Energy Collaborative focuses on critical materials in the new energy economy. And then back here in this space in 2 weeks for our next new energy speaker, we have Churchill Lagutu from ETH Zurich, looking at off-grid technologies in sub-Saharan Africa. So I hope folks will join us for one or more of those. Again, my big thanks to Priya and Justin for today's really informative and useful talk, and all the best to folks. Thanks so much and have a good day.
Thanks, Priya. That was excellent.
Thanks so much, everyone. Have a good day.
Thank you.